We have said that we can apply Ampere's law to solve problems, to compute magnetic fields only for problems with very high symmetry, and we have counted only 3 symmetry types. The first type was the cylindrical symmetry. We have solved many problems there. The second type is the usual infinite solenoid. We have just solved one problem. And that's the last kind. It's the toroid object. And I'm just going to solve one problem in here because we cannot have many variations in there. So in here we have some kind of a torus-shaped object, and a current carrying wire just goes around this object many times. The relevant symmetry is the rotational symmetry. So since these kind of problems are like three-dimensional shapes, I usually have difficulty in drawing correctly the pictures. So as a result, I don't have the perfect pictures in here. So and of course there's also a need for looking at the problem, looking at that shape from different points of view. So as a result, let me just talk about this. So here I just show the torus-shaped object. And of course we have a wire that goes around this torus-shaped object. So I'm going to assume that this wire somehow carries current I in this direction, where when the wire goes over the top of the shape, it goes radially inward, then of course it goes down and then comes back and whatever. So the same wire just goes over the whole shape. So as a result, there are many turns in here. So the relevant variables are basically the current in the wire and the total number of turns. We don't have any turn density in here because the number of turns per unit length might have a different density in the outside and might have a different value in the inside too. But these kind of quantities are not relevant. All right. So as a result, we would like to express the magnetic field at any point in space in terms of these two variables. Let me show another picture in here. So in the first case, of course, I didn't draw all the wires, but in here there are all the wires in here. So the symmetry is the symmetry of rotation. So we are assuming that I'm going to choose, I don't know, the white color. Why not? So if I rotate this object around the z-axis, so the object doesn't change, so the current distribution doesn't change, so therefore the relevant magnetic field that's produced by this object should also should not change under these kind of rotations. So as a result, by using this, we can say something about the magnitudes of the magnetic field at some certain different points. We can say that some of them are equal to each other, but in any case, basic statement is that rotational symmetry. So that's an important part. So at some point we are going to use this argument. Apart from that, there is no symmetry. So I'm going to look at this picture from a different point of view. I think I'm going to look at it from the top and from the side. I don't know which one is next. Yeah, that's the side view. So in that case, the z-axis is the axis of rotation, so that's the symmetry axis. So if I cut this picture like that, then in that case I'm going to see the two cross sections in here. So this cross section in here and the other cross section in here. And of course I also see the half of the whole toroid in here. So there's this part of the picture in here as well. But I didn't want the picture to be crowded, so that I didn't draw that part. In here, you can see in which direction the current is flowing, right? So when the wire is going over the top of the object, it goes inward, then it goes down, and then it goes radially outward at the bottom of the shape, and then up again, and then continues. So as a result, we have the same kind of a thing on that side as well. In any case, this is one picture. I don't know if I want to use this picture or not, so let me erase these additional things. I can also have a top view, so I can look at from this point where the z-axis looks like a point. Right, in that case, z-axis is like that, so that's the top view. So in that top view, the wires are like that, so I can only see the topmost wires. So they are basically carrying current like that. In here, the current is going down, so therefore I put a cross in here. In here, the current is going up, so therefore I'm going to place a dot in here. Right, so each of these is a current carrying wire. All right, so what's the symmetry statement? Let me again erase these additional things. Just keep in mind that these wires are there. So what's the symmetry statement? So let's say that we have a magnetic field in here. By the right-hand rule, by using this picture that Biot-Savart law actually gives us, we can kind of see that the magnetic field at that point is downward, so it's along the minus y direction at that point. So let me call the strength of the magnetic field in here as B. So as a result, rotational symmetry implies that when I rotate this picture, let's say by 90 degrees, so this point is converted into that point and the vector is converted into that vector. So as a result, the magnetic field in here should have a strength B, but it has a different direction, and so on. Can this magnetic field in here have a component along the x direction? And the answer is no, because that would conflict with the Gauss law for magnetic fields, because there are no magnetic monopoles. So as a result, we can rule this thing out. Well, can it have any component along the z direction? I think you can also rule this thing out by considering along the same lines. So as a result, in here, therefore, there's actually only one possible direction for the magnetic field. And so therefore, when you draw the magnetic field lines, you're going to obtain a circular shape in here. A circle which has the same symmetry axis as the symmetry axis of that shape. So the magnetic field lines in here are just circles. And at every point on that circle, B has the magnetic field has the same magnitude. Right, let's also express the other relevant variable in here. So the radius of that circle is r. Let's say it like this. So as a result, the second statement is that the B may depend on r. We are going to see that it actually depends on r. May depend on r. Let's say. So the direction is obvious, so let me not write down a statement about the direction, but the symmetry statement essentially gives us information about both the direction and the magnitude. Now, it is actually kind of obvious how we should choose the Amperian loops in here. I mean, they should coincide with these magnetic field lines so that when I do an integration, I get we get a very simple integral. But let's draw these field lines also in here. So I can imagine them to be inside as well as outside. So there's an inside field inside the toroid, but outside too, they are going to be in the shape of these circles whose symmetry axis is the same as the axis of symmetry of that shape. Okay. So then let me erase all of these details because I want to do a calculation. So first, what I would like to do is this. Let me start with an outside point. So suppose I have a point in here, in the outside. I don't know, let's say it on the ZY plane, let's say. Sorry about this. I am going to use a yellow color for this. There's a point in here, and I would like to know what the magnetic field strength in here is. So at that point, for example, the magnetic field is either along the positive x direction or negative x direction, let's say. So that distance is r. It's the distance from the axis. R is the distance of point from symmetry axis. All right. And I would like to find magnetic field as a function of that distance. What I do is I choose an Amperian loop that's passing from that point, and since I insisted that the Amperian loops should be circular in shape, so as a result that should be a circle like that. All right, let's show this picture in the other picture. So in here, for example, my point is somewhere in there, but in any case my Amperian loop is going to look like that. All right, from this cut picture, probably I shouldn't draw the arrows in there because it's just two parts of the curve actually come on top of each other. So let me not draw any directions in here, but let's just say that this distance in here is the radius of the circle is equal to r in that picture. And in here, let's draw the Amperian loop like that. So let me erase this. All right. I have just chosen the point on the zy plane, so my point is somewhere in here, and I said that the magnetic field is along that direction, probably, and I'm asking for the value of the magnetic field. And to find it, we just choose an Amperian loop like that. Right, it's a circle. And the direction on the Amperian loop is basically, at least at that point, it's parallel with the magnetic field. So therefore, we get a positive line integral, if possible. So the radius in here is r. So what we do is, of course, we just evaluate the line integral. So let me add a page in here. Write down Ampere's law. Right, so it's B dot dl, that's equal to mu 0 times I enclosed. I can clearly see that there is no enclosed current in here, so the right hand side is 0. Left hand side, let's go ahead and look at this picture again. So we have a situation where, let me choose this color first. So we have a displacement on the Amperian loop, which is tangent to the loop, obviously. And at each point also the magnetic field is also tangent to the loop. So therefore these two vectors make a zero angle with each other. So as a result, I'm going to write down this as the dot product as first as the product of the strength of the magnetic field multiplied with the length multiplied with the cosine of the angle between them, and this cosine is 1. So as a result, I have just the integral of b dl. So I converted the dot product into product of the magnitudes. So that's the first step. The second step is that I notice that this is a constant. The magnetic field strength is a constant. So therefore, I can take it out of the integral. So therefore, this is b times dl integral. And then finally, I just noticed that this is just the length of the Amperian loop. So in that case, this is equal to 2 pi r. Right-hand side is 0. All right, so from here, we just say that the magnetic field is therefore 0. So this shows us that the magnetic field outside is equal to 0 in that case. So B out is equal to 0. So in a toroid, therefore, just like in the case of a solenoid, there is no magnetic field outside. All the magnetic field is within the toroid. So as a result, we then pass to the inside. So as a result, I'm going to choose a point somewhere in here. It doesn't matter where, but this is within the toroid. And let me draw some kind of an exaggerated magnetic field arrow in here. So that is supposed to be parallel to the x-axis. Let me redraw again. Or it is along the minus x-axis. I don't know, but from the right-hand rule, we can see that this should be along the positive x-axis. Let me not write down the arrow in here. I'll just write down the magnitude only. And I'm curious about the value of this magnetic field. Again, we draw the Amperian loop as a circle, but this circle is inside the toroid, so it will be somewhere in here. But I'm going to show them in these two alternative pictures. So in this case, it doesn't have to be on the xy plane, right? So let's just say that it's slightly off. So as a result, at this cross section, the Amperian loop is going to look like a dot, and at that point it's going to look like a dot too, but it's actually two diametrically opposite points on the circle, but the circle actually connects these two inside the toroid. All right, so probably that's not useful as well. So let's just look at the top view. The top view is something like that. All right, so the Amperian loop is there. It's not a perfect circle, but in that case, you just have to imagine that this is a circle. So this is the magnetic field that I wanted to find. And of course, there is this geometric parameter in here. My point has a distance of r to the axis. So therefore, this is also the radius of the Amperian loop. All right. So as a result, let's just compute, apply the Ampere's law. So I'm going to write down the Ampere's law, B dot dl, that's equal to mu 0 I enclosed. Let's just say that the computation of the left-hand side is going to be the same. So first we convert it into the product of the magnitudes, take the magnetic field out, and then just write this thing down as the magnetic field multiplied with the length of the Amperian loop. So the right-hand side is, the computation of the right-hand side is important here. So let's just see how it happens. Okay. So we have said that I'm going to use this gray color for showing the wires. So the wires over the top actually go like that, right? But they don't. These wires do not cross the surface enclosed by the Amperian loop. But I have said that after that they actually go downward. So when they are going downward, they cross. So let's see this in the other picture. So here, for example, let me use this thing in here. So the Amperian loop is a circle. So the enclosed surface is a disk. So this red color shows the disk. So let me also erase these axes in here, which have these unfortunate colors. All right. So the red color is the enclosed surface. Okay. Let's look at the direction so that we can decide on the area vector. So by the right-hand rule, the area vector should be pointing downward into the screen. That means along the minus z direction. So therefore, this enclosed surface has a area vector which is pointing downward. All right. So where are the wires? I have already drawn the wires in here, but let me exaggerate. So there is this part of the wire that comes from the top. So this didn't cross the surface yet. But when it is going down, it crosses the surface. And not only crosses, it crosses in the positive direction. So therefore, this is going to be counted as the positive current. Right? In this picture too, let's just show it. Red color shows the enclosed surface. It is that surface in here. All right, I'm scanning it like that. In any case, but I'm going to undo this because I don't want complicated pictures. All right, so this surface is crossed by these current carrying wires. This is one of them, but there are many of them, right? They are all crossing the surface in the positive direction, in the downward direction. And so therefore, since each one of them is carrying a current I, the total current is the number of turns multiplied with I. So as a result, therefore, the enclosed current is the total number of turns times I, and there's a positive sign in front, obviously. Which then tells you that the magnetic field is equal to mu0 n I divided by 2 pi r. Right, that's the magnetic field produced by a toroid. And one question that you might ask is that whether there's a coincidence in here. We have also said that the magnetic field produced by an infinitely long wire also has a similar kind of an expression. So in that case, there are no turns in there. But in that case, we have said that the magnetic field is mu0 I divided by 2 pi r. But that's just a coincidence. A coincidence which basically is due to the fact that the magnetic field lines in both cases are circles. And this 2 pi r factor in here and in here are basically circumferences of these circles. And the numerator of the expressions are coming from the right-hand side of the Ampere's law. Right? There is no similarity between these two problems. They are of different symmetry types. Just keep this in mind. But once all the Amperian loops are determined to be circles, we don't have much options for the form of the equation in any case. So as a result, do not take the similarity of these two cases too seriously. So as a result, in summary, therefore, let me come back to my original picture. So as a result, in here, there's an outside magnetic field which is 0, which means that it doesn't exist. There's an inside magnetic field whose value is given by mu0 n I divided by 2 pi r, where r is the radial distance of the point from the axis of the symmetry, the rotational axis of symmetry of the shape.